Welcome to this lecture. We are talking about the fixed bit regenerator. Today we will try to solve some numerical problem. We have already stated about that problem in the last class, and this is about the heat transfer and pressure drop estimation for packed bit regenerator with the spheres, spherical shots, or it was something like this. It has been made of some lead shot, and its diameter is specified. It's specified. The porosity has already been specified, and it was inside a pipe of diameter 154 millimeter and length 915 mm. So, the gas which is used in this process is nitrogen at a pressure of 2 atmospheric pressure and at an average temperature of 200 Kelvin, and the flow rate of the nitrogen is also specified. So, what we need to find out is the heat transfer coefficient and the pressure drop, which is necessary for any regenerator design. When we talk about the regenerator simulation or design, we will find that these two parameters will be essential to, or it will be necessary to estimate the design, or it will be necessary to simulate the regenerator. So, if we now first concentrate on this packed bed with the sphere and with this particular problem. So, we have been told about certain correlations that we have to use for these packed spheres, and it is the heat transfer is expressed in terms of the Coleman J factor, and then we have also the friction factor given for different Reynolds number region for Re less than 1000 and for Re greater than 1000. So, we can understand that we have to first evaluate the Reynolds number, and then only we will be able to find out the heat transfer coefficient and the pressure drop. And associated parameters for evaluating the Reynolds number, one of them is the equivalent diameter based on the spherical packed spherical spheres. So, then we have to find out what is the mass velocity, and that will be based on the free flow area or the frontal area and the porosity. So, then we have the heat transfer surface area that will also be necessary, particularly and it may be different for the packed sphere, or it is if it is made out of the wire screen. So, here this is the expression to be used for the pressure drop. So, particularly for this problem, if we now look into, we will find that we have the Re value, the dE or the equivalent diameter, and then G the mass velocity. Now, we would like to calculate the first the dE or the equivalent diameter. So, the parameters are known, like the EV is known, ds is known. So, if we put these values, you will find that this will come out to be we have the value of EV, we have the value of ds, and then if you put this will come out to be 6.54 into 10 to the power minus 4 meter. So, this is the equivalent diameter. So, once we know the equivalent diameter, we will come to the mass velocity part, where we know the mass velocity, this is 0.80 kg per second. Then we have this porosity that has been given as 0.38, and the frontal area, obviously you can understand that a frontal will be 4 pi d square by 4. So, this is what is the, and this is of course the this is like a tube which is filled with this kind of spheres, and the frontal area is obviously this surface area, which is nothing but pi d square by 4. So, if we now calculate the free flow area, which will be this frontal area multiplied by this porosity. So, this is pi d square by 4. We have been given this internal diameter, and if we put this value, you will find G will become 11.308 kg per meter square into second. So, this is about the G value. So, we have the value of this equivalent diameter, we have the value of G, and what we need to know is the viscosity part of the fluid. So, this viscosity we have already been told about the fluid. The fluid is nitrogen at an average pressure of 200 Kelvin, and its temperature is pressure is already known. So, at that temperature and pressure, we have to evaluate the velocity properties of nitrogen, and mu will come out to be we will put its value, it is 12.95. So, if we now put this G is equals to 11.308 multiplied by equivalent diameter was 6.54 into 10 to the power minus 4, and then we have the mu equals to 12.947 into 10 to the power of minus 6, and then we get the Reynolds number to be 571. So, now we know the Reynolds number, and once we know the Reynolds number, we would be able to decide whether we will use which correlation we have to use for the friction factor, and we already know that the correlation for the Cold-1 J factor. So, now if we go back to our discussion, now we will come back to the heat transfer coefficient in the form of Cold-1 J factor, and this Cold-1 J factor is basically nothing but 0.23 into R d to the power 0.23 multiplied by R d to the power 0.23. So, here we will also put the other parameters, and then we will see how we will go about it. Okay. So, here it is, if we put in this correlation, we will find that this is 0.23 and the R e is 571 to the power 0.3 to the power 0.3. So, this will come out to be 0.034256. So, this would be the value of the Cold-1 J factor, and the Cold-1 J factor is nothing but the Stanton number and Prandtl number to the power 2/3. The Stanton number is H by GCP. So, we already have an idea about the G already we obtained. Now, we also know from the fluid properties of nitrogen the value of Cp. So, we can calculate the heat transfer coefficient, that is what we are looking for from this relation. So, this is already known 0.034256, and then that is equals to H by G is 11.308, and then you have the Cp value. Cp is already known because we know the temperature and pressure of the fluid, and Cp will become H by G Cp. Cp value is 1.04 into 47 into 10 to the power 3 joule per kg Kelvin. So, this is the value of Cp, and once we put this value, and we have also the value of Prandtl number, Pr is equals to 0.72567. So, this is the value of the Prandtl number. So, we have to put that Prandtl number here 0.72567 to the power 2/3, and accordingly we will find that the heat transfer coefficient will come out to be 502.7 watt per meter square Kelvin. So, this is what is needed for this heat transfer, that is what we are looking for. Then we will go for the friction factor, because we have seen that the Reynolds number is less than 1000. So, we will put it in this relation, and from there we will be able to estimate the friction factor. So, the friction factor is coming to be 2.346. If you put the R D is equals to 571, that is what we have estimated for this problem. And once we know the friction factor, we can put all these values over here. The friction factor already we have known is it has already been obtained. The length of the heat exchanger is the regenerator has already been told. So, its the length is 0.914 meters, and then G value is known. The equivalent diameter we have calculated. The density, since the nitrogen is flowing at a temperature at an average temperature of 200 Kelvin and 2 atmospheric pressure. So, the density of the gas is also known, and this density is equals to 3.428 and kg per meter cube. So, if we put all these values in this relation, we find that this will come out to be 61173 kPa Pa, and that will be equivalent to 61.1 or 2 kPa. So, we can estimate the pressure drop for this packed bed for a flow rate of the given flow rate of the flow rate was given 0.08 kg per second. We find that the estimated pressure drop is 61.2 kPa. So, like that we have to depending on the regenerator matrix material, we have to calculate the pressure drop and the heat transfer coefficient as it is necessary for the design on the simulation. So, now we will go back to our discussion on the simulation of the regenerator. Here comes a problem. We have taken it from the Barron's cryogenic heat transfer book, and it is a valve type regenerator, fixed bed regenerator. It is made of say 1.182 kg metal spheres, and its material properties are known. So, it is both the specific heat and the thermal conductivity of this material has already been given. The porosity of this is also known, and it is made of packed bed spheres, and heating cooling periods are equal, and the total time period is 4 seconds. So, the hot period is 2 seconds and the cold period is also of 2 seconds. The fluid flowing through this system is helium. So, its Cp is also given, and the hot helium flow rate is 40 gram per second, whereas the cold helium flow is slightly less than that, and it is 36 gram per second. The heat transfer coefficients we need not calculate, it has already been specified. You can understand that depending on the situation, or like here already the flow rates have already been given, and we need to calculate as we have specified, just we have to use similar expressions to calculate the heat transfer coefficient on this and the heat transfer coefficient on the cold side and for the hot stream and the cold stream. And its heat transfer surface area is also known. So, as you can understand that it is pretty similar to the heat exchanger design process, where or design of the simulation process, particularly this is we are talking about the simulation, where we find that the simulation is about I mean a situation where we try to find out the performance of something where all the parameters related to its configuration or the geometry is already known. Here as we can understand that the materials property are known, I mean the heat transfer surface area is known, its other properties are known, so that we can calculate the heat transfer coefficient. So, this is also known, and what we find is that what we need to know is the effectiveness. So, that heat exchanger effect regenerator effectiveness we need to calculate, and we have been told about the other parameters. So, now as you can understand that some of the parameters are given, and what we have to find out is the regenerator effectiveness and what would be the process to do that. So, we will discuss about it in the next slide. So, first of all we need to find out what is the minimum capacity fluid flow, and for that we of course need to find out the Cp value of the gas flow, and already it has already been told the Cp of helium has already been given. So, we can understand that we will be able to find out the C mean. So, the heat transfer coefficient and the heat transfer surface area is also given. So, the NTU can also be calculated. So, once we know the NTU, we would be able to calculate the ratio I mean the Cm, that is the capacity rate ratio. So, here once we know the Cm and NTU, and also we need to find out the depending on the value of the Cr, if it is not 1, we have to find out an equivalent NTU and equivalent Cme or the capacity rate ratio. So, depending on that we will be using this chart for the given as a function of NTU and Cm, and that on the basis of NTU effective values and Cme effective. So, we will try to find out the epsilon, and once we find out that epsilon, we know that we have to calculate a factor x, and depending on that x we will be able to find out the correlation. We will be using this correlation to calculate this regenerator effectiveness. So, this is the procedure that is to be followed. So, we will go one by one in this case. So, here what we do is, first of all sorry, we will go back to our earlier slide. So, here we would go to this calculation. First of all, we know that what are the property values that is given. So, here we find that this regenerator is made of Cp is already given. So, first of all we will find out the Ch. So, that is equals to Mh and Ch, and that comes out to be 0.04 is the mass flow, and then we have the corresponding 5.2 the specific heat, that is this many kilojoule per kg Kelvin, and we have this is kg per second. So, if we multiply these two parameters, this comes out to be 0.2080 then kilowatt per, this is kilowatt per Kelvin, and we can also calculate the Cc. So, this will become Mc and dot, and then Cc, then what is Cc? Mc dot is slightly less, and it is 0.36. So, 0.036 multiplied by 5.2 kilojoule per kg Kelvin, and then you have for this one this many kg per second. So, this comes out to be 0.1872 kilowatt per Kelvin. So, you can understand that this is the C mean, and the cold fluid stream is the C mean fluid, and this is the C max fluid. So, we can now try to find out the CR, that is equals to C mean by C max, and that will come out to be 0.90. So, this is not equals to 1. So, we know that the capacity rate ratio Cm equivalent we have to find out. We have to also find out the NTU equivalent. So, we will find out the appropriate relation to calculate the CME and NTU effective, and then we will proceed to the calculation of the values of the effectiveness. So, now if we try to calculate the NTU, we know that NTU is already its NTU value is given by 1 by heat transfer surface area 1 by H AC C plus 1 by HH AH. This basically this is nothing but UA by C mean. So, this is the value of C mean, and this is nothing but this is UA is 1 by HC AC AH to the power this one. So, this is in this case we have seen that both the HC AC and AH are the same. Here the HC is equals to HH is equals to 8320, and AC is equals to AH is equals to 0.950. So, basically these two terms are getting added, and the NTU becomes say 1 by what is that 187.2. This kilowatt per Kelvin we have converted into watt per Kelvin, and then we have this 2 by this 8320 multiplied by 0.95. So, this whole to the power minus 1 will give you the value of NTU equals to 21.11. So, once we know the NTU value, we would be able to calculate the NTU effective value, and that NTU effective value will become will use that expression that we have already talked about. So, the NTU effective value comes out to be 20. Okay. And then we have also, now we need to, as we have said, the matrix capacity rate ratio, that Cm, that is equals to, it is 1.882 multiplied by 0.840, and that is the total time for, and then you have to divide it by 0.1872. So, then we have this will come out to be 2.111. Now, we have the equivalent CME, then you will find that it is coming nearly to be 2.0, and then if we now have the value of this effective NTU and the effective value of Cm, that is equals to 20 and 2, and the corresponding value for the epsilon, that would become from there we will get an epsilon is equals to 0.935. So, we now have an estimate of the rough estimate of the effectiveness, because we have used that chart which corresponds to CR equals to 1, but since the CR is not equals to 1 for us, we have to find out this effective value for corresponding to this effective CME and this NTU effective value, and that there we are getting the epsilon 1. So, as we have said earlier that based on this value we will be calculating the parameter x, and that parameter x comes out to be 1.5184, and you already have told it about the expression of x, and from there if we now put the value of that one, and the corresponding epsilon would be 1 minus c to the power minus x divided by 1 minus CR into e to the power minus x. So, this is nothing but if we put the value of x in this expression, you will find that this is 9727. So, the regenerator is 97.27% effective, or in its ineffectiveness is basically 0.0273 or 2.73%. So, this is how we estimate the effectiveness of the regenerator or simulate the performance of any regenerator in a nutshell. Thank you for your attention.